All right, continuing on, here we are, chapter 2.4 review questions. We got two of them, and you can expect for sure you're going to have a question like this where you have to graph a rational expression. You know for sure because we're having questions from every chapter, and chapter 2.4, that's all I'm really asking you to know, so guarantee you're going to have one of those. Okay, let's look at it, number 9. And you got this function here, f of x is 2x over 1 minus x squared, and what we're going to do is just factor that. 1 minus x squared is a difference of squares. So that's 1 plus x and 1 minus x. Or if you prefer, if you want to, you could switch it around and say, okay, that's x plus 1, right? And this is x minus 1 if you just factor out a negative 1 on the outside. And that negative 1 you can put at the top if you like. So it's kind of preference. So if you want to make that change, this looks something like something maybe you're more familiar with, where we have the x's in front. Actually, now that I think about it, yeah, I kind of like this version better myself. So let's stick with that one. It will still work if you kept the original version like that as well. Okay, let's find vertical asymptotes. That's part A. So vertical asymptotes come from when the denominator is 0 and the top is not 0. So we've got vertical asymptotes, VA for short, at x equals to negative 1 and x equal to positive 1. Those are the two things that make the denominator 0. And then moving on to letter B, switch colors here. Horizontal or oblique asymptotes. Okay, so in this case, we have the top with the degree 1, right? And the bottom, you have 2 x's. So that's like the x squared, which means the bottom has a higher degree than the top. And so you have a horizontal asymptote at y equal to 0. Okay, so that's part B. Part C, complete the statement. As x goes to negative infinity, what happens to f of x? This actually follows from part B, and part C and D actually both follow from part B. Because if you have a horizontal asymptote, what happens is your function is going to approach those horizontal asymptotes, right? So as x approaches negative infinity, as it goes far to the left, well, f of x is going to approach that 0, the horizontal asymptote, right? Okay, I just realized I did not capitalize. So let's do that. As x approaches positive infinity, same thing happens, right? F of x is going to approach that horizontal asymptote at 0. Okay, moving on to letter E. State the domain of the function. Okay, easy. Domain. It's just everywhere that you're defined here, and it's going to be everywhere except where you have those vertical asymptotes in our case. We don't have any discontinuities that are removable because there's no instances where the top and bottom have the same shared 0. Yeah, so that means our domain is basically everything negative infinity up until you hit that first negative 1, and then union from that negative 1 to the positive 1, and then again from that positive 1 to infinity. Or alternatively, you can just say x cannot be negative 1, x cannot be positive 1, and everywhere else is okay. So these are two different ways to represent the same thing. And finally, sketch the function. Okay, but I feel like actually there's kind of something missing here. Before we sketch, we should also find the zeros. That's going to give us a better picture. So what are the zeros for this? It's pretty obvious right here, right? It comes from when the top is 0, which would be x equal to 0. So this is just a note for myself. It's 0 at x equal to 0. The function is. Okay, so before we go to graph, let's just kind of do a quick chart. Where are we above or below the axis in reference to the 0, which happens at 0, and also to the asymptotes, negative 1 and positive 1. Okay, so to do that check, we're going to just use test points. So let's use obvious ones. Negative 2 would be an obvious one. Here, negative a half would be between those, easy to check. Positive a half, and then positive 2. Those are the points we're going to check. We just want to know if it's positive or negative to get a rough sketch. And what am I looking at? Just to remind you one more time, we're looking at this function here, right? So let's take a look at that guy. Starting with negative 2. What happens if I plug in negative 2? Okay, negative 2, plug in negative 2. Negative 2 times negative 2, that's going to be a positive value, right? If I plug in negative 2 over here, that's going to be a negative value. And if I plug in negative 2 there, negative 2 minus 1, that's going to be a negative value. Oops, negative value. So overall, positive on the top, negative on the bottom makes a positive. So overall, this should be positive. Okay, let's get rid of all this stuff. Okay, so once again, I'm focused on this thing right here, yeah? This is the function I'm using to test. Actually, you know what I'm gonna do, guys? I'm gonna bring it closer so my eyes don't have to keep tracking back and forth. Let's just bring it down here. Oops. And then we'll track positive or negative down here. All right, so next one will be negative a half. What happens if you put negative a half? Negative a half over here times negative 2, that would be a positive value. Negative half plus 1 over here would be a positive value as well. Negative half minus 1 would be a negative value. So overall, this is a negative. Negative over there. Okay, next one. I'm going to go ahead and just leave the highlights off so it's easier for me. Okay, now if I plug in a positive half would be negative here. Half plus 1 would be positive there. Half minus 1 would be negative there. So overall, that's negative, negative, positive. That's 2. Negatives makes a positive. I shouldn't be using black because it's getting confusing, yeah. Over here, I mean. Okay, what if I plug in 2? 2 times negative 2 is going to be negative up top. 2 plus 1 is positive. 2 minus 1 is positive. So overall, it's going to be negative. Negative. Okay, so now that I know the signs of everything, let's go that way. Actually, let's get rid of it. Then we're ready to draw our graph. It's ready to do the sketch here. So to do the sketch, first I'm going to start off with the XY axes, and then I'm going to draw my asymptotes, starting with -1. X equal to -1 would be right here. -1, draw a line. Ooh, that's a crooked line, but that's okay. +1 right there. Oops, missed. Try again right there. Okay. So +1, -1, and then also horizontal asymptote. So I'm just gonna dot this part here. Horizontal asymptote at y equal to 0, right? So I'm just gonna kind of indicate I have one there. Okay, and let's plot the points. You know, the zeros are at 0. So the 0, right? Dead center, yeah. And then let's do a graph in blue. Let's just follow our negatives and positives and approaching the axes. So it's positive on the left. That means it should look something like this, right? And on the right, it's negative. So it should look something like this. Approaching the asymptotes on both sides. And then in the middle, I'm going from negative to positive. So something like this. Approaching the asymptote, hit that 0, and then switch to positive. All right, so there's your general picture. Okay, just as a quick check, let's just graph this thing. It's 2x over 1 minus x squared. This is 2x over 1 minus x squared. And yeah, that is how it looks. Yeah, roughly same shape as what we have over there. Sweet. That's pretty cool, huh? I mean, the fact that we can distill the general shape of that rational expression and find all the pieces, that's pretty satisfying to me. It's like it's a pretty satisfying end to like this little math puzzle thing. Okay, let's go to the next question, number 10. Slightly harder one, but you know, still within the realm of something that you could potentially be asked. It's not so bad. Okay, so we've got fx equal to x cubed minus 4x over x cubed minus 9x. First thing I'm going to do is just factor out that x. So it's x times x squared minus 4. And the bottom is x times x squared minus 9. And that's an obvious difference of squares up top and bottom. So this is x plus 2, x minus 2, right? And the bottom is x plus 3, x minus 3. Okay, and you got an x on top and bottom. So we see, okay, I'm gonna cancel these x's, and you get all excited, and you get excited, right? And you say, oh, this is equal to x plus 2, x minus 2 on the top, and x plus 3, x minus 3 on the bottom. But when you do that, don't get too excited. You have to remember to account for what that cancellation you made was. So what I mean by that is you have to say that these are in fact equal, except when x is equal to 0. Because when x is 0, you're still undefined at the bottom, right? Because you're dividing by 0. So x cannot be 0. And that's where we get this removable discontinuity. So for all intents and purposes, these guys are going to be equal, except for that one place where x is equal to 0. Okay, and now let's go to the next step. So first question, vertical asymptotes, yes. Right at the where the bottom is 0, right? Where x equal to -3, x equals to +3. Quick question to you guys. What about x equal to 0? Is that a vertical asymptote? Ask yourself that question. Pause if you need to. And the answer to that is no, it's not. It's not. It's a removable discontinuity. But if you look at this final reduced version, it's not pure. There's no x in the bottom, right? So it's not a vertical asymptote. Okay, part B, horizontal asymptote. Okay, so looking at this guy, notice they're both basically cubed, right? Up top and bottom. Actually, let's look at the original here. You see you have a cube term as your leading leading term, sorry. And you've got a cube term on the bottom leading terms. And they both got a 1 in front of them. So to check horizontal asymptotes, if they're both same power up top and bottom, you just divide the leading coefficients. In this case, it's both 1. So 1 divided by 1 would be 1, which means your horizontal asymptote is just y equal to 1. Yeah, the coefficient for this is a 1, coefficient for that is a 1. 1 divided by 1 equal to 1. That's where we get our horizontal asymptote in this case. So remember the rule, yeah? If the bottom power is higher than the top, and that's when you get a horizontal asymptote y equal to 0. If they're the same, you divide the leading coefficients. And if the top is 1 higher, then you divide and you get the oblique asymptote as a result. Okay, so where are we at now? That was part B. Let's go on to part C. And part C and part D, these are follow-ups to part B, right? What happens is x goes to -infinity. Well, f of x is going to approach that horizontal asymptote. And same thing as x approaches positive infinity, f of x is going to approach that same horizontal asymptote. Okay, letter E, state the domain of the function. Okay, domain is going to be everything except for these vertical asymptotes and also this discontinuity that we have. So, easy way to say this is just to say x cannot be -3, 0, 0, or +3. If you want to write it as interval notation, -infinity to -3, union with -3 to 0, union with 0 to 3, union with 3 to +infinity. So 2 different ways of saying the same thing in letter E. Okay, so one or the other means the same thing. Okay, letter F. Okay, we're on to sketching. But, before we sketch, like I mentioned in the previous similar question, we should find our zeros first. So zeros are when the top is 0, which would be -2 and +2. Yeah, when x is equal to -2, +2. All right, let's make our little table here. This is a number line representing the realm of possibilities for x. We want to plot here our asymptotes as well as our zeros. So here we have -3, we've got -2, we've got +2, and we've got +3. Right, those are the vertical asymptotes or zeros. And we're going to do test points in between them. So let's do a test point here at -4. Do one at -2.5. Here we can do one right at 0. And I know you might be saying to yourself, well, 0 is not strictly speaking defined, right? It's true, it's not. But we can actually just graph this portion as if it was defined and then just leave a little hole where we're at 0. And that's actually going to be important for us to know that spot anyway, because then that's when we know where to put that hole. Okay, so also we're going to check 2.5 and then +4. So those are the 5 test points that I'm going to use. And what am I using for what am I testing? I'm testing this expression right here. So let's copy that expression. I'm just going to write it down again down here. This is x plus 2, x minus 2, x plus 3, and x minus 3. And all I care about right now is just positive or negatives, except for at 0. I do want to know what the value is at 0 because I want to plot that nicely. So let's check though. -4, what happens at -4? -4 plus 2 is negative. -4 minus 2 also negative. -4 plus 3 negative. -4 minus 3 negative. So negative, 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 negative makes it overall positive in that region. Yeah, positive. I've got 4 negatives makes it positive. It's even number of even number of negatives. Okay, negative 2.5 plus 2, that's a negative. Negative 2.5 minus 2, also negative. Negative 2.5 plus 3 is actually positive, and then negative 2.5 minus 3 is negative. So overall, that's going to be 3 negatives, making this area negative. Okay, what do I get if I plug in a 0? And here I'm going to get the actual numbers. If I plug in 0, this is going to be positive 2. 0 minus 2 is negative 2. 0 plus 3 is going to be 3. And then 0 minus 3 is negative 3. So that's going to be equal to negative 4 up top, negative 9 down bottom, which is 4/9. So not only is this positive, but this is equal to 4/9. Okay, that's going to come into play at the end when you graph, and you'll see what I mean when we get there. Okay, shucks, this is getting a little messy because you're kind of in the way there, guy. So just move you up just a little bit. Okay, so now next test point was 2.5, yeah, checking 2.5. 2.5 plus 2 would be positive. 2.5 minus 2, still positive. 2.5 plus 3, positive. 2.5 minus 3 is negative. So overall, that's going to be negative next. Negative over here. Okay, and lastly, at 4, let's check 4. So 4 plus 2, positive. 4 minus 2, positive. 4 plus 3, positive. 4 minus 3, positive. So overall, positive. So positive, negative, positive, negative, positive. We're just basically switching signs each spot, yeah? All right, we're ready to graph. Erase this expression now. Let's do the graph. Here's our sketch. Y-axis, x-axis. Here's x, here's y. And let's start with our asymptotes. Asymptotes were at -3 and +3. 1, 2, 3 there. 1, 2, 3 there. And I got there's asymptotes there. Okay, I also had an asymptote at y equal to 1. So that's right over here. Something like that. Okay, and then on the left side, we're positive. So our graph is going to look something like this. And on the far right side, we're also positive. So something like this. Yeah. So I just checked out, I just completed this region here. Sorry, this region here. And this region here. I just kind of started at the ends. Okay, in between, let's plot our zeros as well, guys. So zeros are at -2 right here and +2 right there. Yeah. If you want, you can label this -3, -2, -1, 1, 2, 3. Okay, and then we're negative approaching that first one, positive in the middle, and then negative. And then remember, we should be at 4/9 right at 0. Okay, I know you're saying again that it's not defined there, and you're correct. So 4/9 is slightly less than half. Yeah. So that would be right here, right? Except what you actually have is you have a little hole there because it's not defined. So I'm going to put a little hole for myself. 4/9. So you're right there. Yeah. And then you're negative going in to this 0. Positive in between. You hit that little discontinuity there, which is a hole. And then you go back down to being negative. So it looks like this. Approaching the asymptotes, right? And right there in the center, you got a little hole. And that accomplished what I wanted it to accomplish, where I'm negative here, positive in the middle, and then back to negative. Yeah? Negative, positive, negative. Okay, so that's a sketch. That's a sketch. And let's confirm it. Let's check out the graphing calculator. I have it preloaded here already. And yeah, that is what it looks like, right? You can't see, but if I try it. Okay, yeah. So if I move this cursor along here, right as I hit 0, see it says undefined right there. Yeah. So that's right about where I was. And 1 is 1 is right there. So it's right below half. See that? So just as I basically had graphed. Oh, one other thing I noticed, guys. So this is kind of this one turns out to be symmetric, right? And you could have actually determined that previously just from the algebra by looking at that x cubed minus 4x divided by x cubed minus 9x. And I know it doesn't look like it's an even function, but if you plug in f equal to if you plug in negative x into the function, you're gonna see that it actually turns out correct. So here's a little bonus to the video. You don't have to watch this part because we already finished the question, but here's a little bonus. Here's a bonus. Check this out. What's f of negative x? That'll be negative x cubed minus 4 times negative x. The bottom is negative x cubed minus 9 times negative x. And let's do a little simplification here. That's negative x cubed plus 4x over negative x cubed plus 9x. Let's factor out a negative 1. That's x cubed minus 4x over negative 1 x cubed plus, minus 9x. Okay, and then those two negative 1s, well, we can cancel them out, leaving us with x cubed minus 4x over x cubed minus 9x. That's the same thing, right? So f of negative x turns out to be the same as the original, which confirms that we do in fact have an even function. So now looking at the graph, it makes sense, right? Because this guy, symmetric across the center. You see that? Symmetric over that center line. Beautiful. All right, guys. See ya in the next video.